Hi, we now continue with our study of probability theory. We do so by looking at the addition rule. This is the first of several rules you're going to have to learn. So let's get started. In this example, we're given results from tests for marijuana use. So you have 300 people who participated in this test. Some of them actually do use marijuana, some of them do not. Some of the people that took this test received positive test results and some of them received negative test results. One of the main things that stands out with these results is that the fact that you used marijuana does not necessarily mean you will get a positive test result. The fact that you do not use marijuana does not necessarily mean you'll get a negative test result. So look at the results here. Right, so pause and look at these and think about it for a moment. So let's identify some events here then. So you have the event A that we will say, well, the event is this, the subject used marijuana. B, the subject did not use marijuana. C, the subject had a positive test result. The subject had a negative test result. You're asked to find the probabilities of each event, and you're also asked to find the probability of randomly selecting a subject who used marijuana or tested positive. In other words, find the probability of A or C. So the probability of A, the subject used marijuana, well, we need to find out how many people actually used marijuana. And so we get 122 people actually used marijuana. Out of 300 in all, that gives us a probability of 0.4067. The probability that the subject did not use marijuana, well, how many did not use marijuana? 24 plus 154, that's 178. So the probability that the subject did not use marijuana was 0.5933. The probability that the subject had a positive test result, well, how many people received positive test results? 119 plus 24, that gives us 143 out of 300, 0.4767. And D, the probability that the subject had a negative test result, well, it's these 3 plus these 154, that gives us 157 out of 300 for a probability of 0.5233. Now we're asked to find the probability of A or C. So let's look at this. We need to get the people who used marijuana or who tested positive. So the people who used marijuana are these 122 here. And the people who tested positive are these 119 plus 24. That's what gives us what? 119 plus 24, 143. But what happens here is that we have counted these 119 people twice, so we have to subtract 119. So this is very important. Another way to have done this would have been to simply say, well, the people who meet this criteria are the numbers here, here, and here, right? We want the people who test positive or use marijuana. So that's these people and these people here. And so you could simply have said, well, 119 plus 3 plus 24. So just pay attention to this, right? And see that these are equal. In the end, you get 146 out of 300, which is 0.4867. This brings us to the formal addition rule. If we have two events, A and event B, then the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So the probability of A and B denotes the probability that A and B both occur at the same time in a given trial or procedure. So let's look at this and see what that implies here. Here we're using the events A and the event C. So the probability of A or C, and this, remember when we talk about or, we're looking at the union of two events. And so here the probability of A plus the probability of C minus the probability of A and C. So the way we talk about A and C is to say the intersection of these two sets. So this is very important. And so how do we continue here? This will then give us 119 plus 3, that's 122 over 300. and the probability of C is 143. We have already found these here. 143 over 300. And then the probability of A and C, well, that's the probability of having used marijuana and having a positive test result. So that's this number here, 119. So you see how it works out. We are subtracting. This is the same thing. Notice I can have, that's this here. We have the same common denominator here, 300, and then this is 122 plus 143 minus 119. And of course this is going to give us then 146 over 300. So let's look at this example now. A coin and a die are thrown together. Find the probability of obtaining a head. A number greater than 4. A head and a number greater than 4. A head or a number greater than 4. So let's look at the sample space. You can get a head and 1, head and 2, head and 3, head and 4, and so on. And then you can get tail and 1 up to tail and 6. So what's the probability of getting a head? Well, it's this event. Let's say the event getting a head. Let's say I call it A. Well, this is a subset. It's this subset of the sample space here. What's the probability? What's the event getting a number greater than 4? Well, it's this subset of the sample space. Notice the numbers are all greater than 4. So you can get head and 5, head and 6, tail and 5, tail and 6. So what's the probability of getting a head and a number greater than 4? Well, first let's find the probability of getting a head, which is what? The cardinality of this set, which is 6, out of the cardinality of the sample space, which is 12. That gives us a half. Probability of B is the cardinality of this set, which is 4, divided by the cardinality of this set, which is 12. That's 2 out of 6, 1 out of 3. So getting a head and a number greater than 4. Well, we want the intersection of these two sets. So later on we look at this in more detail. But for right now, let's just look at this. Getting a head and a number greater than 4. Well, these are all cases where we get numbers greater than 4. These are all cases where we get head. So what's the intersection here? Well, head and 5, notice this belongs to both sets, and head and 6 belongs to both sets. Which means then that the probability of getting a head and a number greater than 4 is 2/12, which is equal to 1/6. So notice the problems are getting a little bit more, not too complicated, but a little bit more, a little deeper, a little bit more profound. So make sure you understand this. And getting a head or a number greater than 4. So in this case, we want the union of these two sets. So that's the union of the two sets. And then what's the cardinality of this union? Well, it's 8. Notice there are 8 members here. So the probability then of getting a head or a number greater than 4 is 2/3. So take your time and make sure you understand this. After a while, these problems are going to get difficult and you're not going to be able to, as people like to say, common sense the problem. You're going to have to really understand and apply these principles. Let's check this rule here. Does the rule actually apply here? Well, what's the probability of A or B? The probability of A or B is 2/3. That's 2/3. And this we say is equal to the probability of A plus the probability of B minus the probability of A and B. Well, what's the probability of A? That's 1/2. What's the probability of B? That's 1/3. What's the probability of A and B? 1/6. If you do your little calculation here, you can see that you do indeed get 2/3. So here we've, in a way, verified this little rule here. In this example, we're given two events, A and B, such that the probability of A is 19/30, the probability of B is 2/5, and the probability of A or B is 4/5. You're asked to find the probability of A and B. So we can use this very same equation here, and all we have to do is rearrange it. So we can simply say then that the probability of A and B is the probability of A plus the probability of B minus the probability of A or B. So this is just some very basic algebra, so I hope this is not hard for you to understand. And now we just plug in our numbers here. That's 19 over 30 plus 2/5 minus 4/5, and we get that the probability of A and B is 7 over 30. Bear in mind, for all these examples here, we're talking about the probability of A and B occurring in the same trial, right? So in a single trial, we have both of these events occurring. In this example, we're told that in a group of 20 adults, 4 of the 7 women and 2 of the 13 men wear glasses. What is the probability that a person chosen at random from the group is a woman or someone who wears glasses? So let's organize our data in a way that we can get a better insight into what's going on here. So we know that we have 20 adults in all. We also know that we have 7 women and that 4 of them wear glasses. So we make this little table here, and we have wears glasses, does not wear glasses, man, woman. And so of the 7, 4 wear glasses. So we calculate this 3. So how do we get this 3? Because we know there are 7, and well, if 4 wear glasses, 3 will not. Likewise, we know there are 13 men and 2 wear glasses, so 11 will not. Now we look for some events. And of course, the events will be the person chosen is a woman, and the event B will be the person chosen wears glasses. So what we need to do now is find this probability. So the probability of A or B, note union, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So this is a probability that the person selected at random is a woman. This is the probability that the person selected at random wears glasses. And this is the probability that the person selected at random is a woman and wears glasses. So make sure you understand this. So this probability is 7 out of 20. 7 women. This probability is 6 out of 20. Notice 6 wear glasses. Of course, how many are women and wear glasses? Well, that's going to be these 4 here. 4 out of 20. And so we set this up and we get 9 out of 20, which is 0.45. Of course, you could also have gotten this answer from inspection. The probability of randomly selecting someone who is a woman or wears glasses is 2 plus 4 plus 3. That's 9 out of a total of 20. But still, it's important that you learn to see it this way. Mutually exclusive events are events that have no elements in common. In other words, they are disjoint sets. There is no overlap. So let's look at this example to begin to get a better understanding of this idea. Consider the procedure of randomly selecting one of the 300 subjects included in this table. Determine whether the following events are disjoint, that is, mutually exclusive. Getting a subject with a negative test result, getting a subject who did not use marijuana. The question you need to ask is it possible to get someone who has a negative test result and did not use marijuana? Well, yes, that's these 154 here. So these two events are not disjoint. They are disjoint if it's not possible to get both events occurring at the same time. Here it is possible to get somebody who tests negative and who does not or did not use marijuana. Assuming that one person is randomly selected from the 300 people that were tested, find the probability of selecting a subject who had a negative test or did not use marijuana. By inspection, we could see that the people who did not use marijuana are all these people here. The people who got a negative test are all these people here. So we could simply say 3 plus 154 plus 24 divided by 300. But let's break this down so we so we practice our understanding of the theory here. The probability of a negative test result, or did not use marijuana, and I forgot to put the parentheses here. Okay, so here is the parentheses. This probability is the probability of what? Getting a negative test result, which will be 157 out of 300, plus the probability of not using marijuana, which is 178. That's the sum of these two numbers here, divided by 300, minus the probability of getting a test that is negative and not having used marijuana, which is 154 out of 300. And we get, or 181 divided by 300, which is 0.6033. So remember these, so note these are approximations, right? I'm rounding off to 4 decimal places. Here we are given that in a race, the probability that John wins is 1/3, the probability that Paul wins is 1/4, and the probability that Mark wins is 1/5. Find the probability that A, John or Mark wins, B, neither John nor Paul wins. Assume there are no ties. This is very important. So let's find some events here. We'll just say J is the event that John wins, P, that Paul wins, M, that Mark wins. So this is what we're told. We're told that the probability of John winning is 1/3, of Paul winning is 1/4, of Mark winning is 1/5. Here now we're asked for the probability of John or Mark winning. That's the union of these two events here. Now we can simply add them. Why do we not have minus the probability of John winning and Mark winning? Because it's not possible. That is why this is so important. There are no ties. So they can't both come in first. So notice the rule for addition becomes simplified in the case of mutually exclusive events. In this case, we are asked to find the probability that neither John nor Paul wins. So let's take a look at how we can say that. This is one way we can say this, that this is the probability of John not winning and Paul not winning. The way to find this is to find the complement of this and subtract it from 1. This is the event in which Paul does not win. In other words, this includes all the outcomes in which Paul does not win and John does not win. The complement of this will be all events in which either John wins or Paul wins. And so the probability of this event is going to be 1 minus the probability of this event. And of course, this is easy to calculate. That's 1/3 plus 1/4. That gives us 1 minus 7/12. The answer then is 5/12, or 0.4167. So the probability of an event is equal to 1 minus the probability of its complement. In this case, we are told that a card is drawn at random from an ordinary pack of 52 playing cards. Find the probability that the card is A, a club or a diamond, B, a club or a king. So here we have a picture of an ordinary deck of cards. So we want to find the probability that the card is a club or a diamond. So notice we have what? 52 cards, we have 13 clubs, 13 diamonds. But before we get into that, let's take a look at our sample space and our events. So the sample space here has a cardinality of 52. There are 52 cards. The event, picking a club, well, its cardinality is 13. Notice now we're not actually writing out all the members, although I must say they are here. No? These are all the clubs, 13 of them. The cardinality of the event getting a diamond is 13 also. There are 13 of them. And the cardinality of getting a king is 4. Notice there are 4 kings. So if we want the probability of getting a club or a diamond, well, that's the union of these two events. Now they are mutually exclusive. That's why we can use this simplified calculation of this event. It's the probability of getting a club plus the probability of getting a diamond. 13 out of 52 plus 13 out of 52, that's a half. How about getting a club or a king? Well, that's this here. It's a probability of getting a club plus the probability of getting a king minus the probability of getting a card that's both a club and a king. Notice there's one of them, and that's the king of clubs. See there? This card. Okay, so that gives us then 4 of 13, that's 0.3077. So it is important that you be able to realize from the context given to you how to approach answering these questions. Before we end this discussion, let's review complementary events. The complement of an event A, denoted with this notation, consists of all outcomes not in A. Simple as that. Complementary events then are by definition mutually exclusive. And so we have used this in the past to solve various questions. The most notable was this one here. So go over this. So the probability of an event plus the probability of its complement will always be equal to 1. So this is the main idea that you need to remember. These can be reasoned to simply from this, right? Basic algebra. So here's a Venn diagram representing this idea. So this is some event A, this is the entire sample space. The probability of what is not A is 1 minus the probability of A. Simple as that. And we have seen this example before. So in reality, when a baby is born, the probability of getting a boy is 0.512. Find the probability of not getting a boy. So we can do this by saying then the probability of not getting a boy is 1 minus the probability of getting a boy. So that's 0.488, which happens to be the probability of getting a girl. So a major advantage of the rule of complementary events is that its use can greatly simplify certain problems, and you will see this a little bit later on, right? Problems that would seem very difficult are made very easy because of this concept. Okay, so that's it for this little discussion here. Bye for now.